Good afternoon. My name is Matt Gretton-Dan. I'm the product manager for the architecture at ARM, which means that I'm able, allegedly, to talk about ARM architecture improvements and enhancements that we've done in 2018. The too long didn't read version of this presentation is ARM 8.5. So yes, who am I? As I said, I'm product manager at ARM. My history is that I've been at ARM now 14 odd years. I started out in compiler engineering. I've had a long history with Linaro. I led the toolchain working group for 18 months a couple of years ago. And so, yes, then coming here. So it's nice to be back. Connect has changed and not changed at the same time. Nice to see so many familiar faces. And why am I here? Well, it says on the screen, talk about ARM architecture developments in 2018. I want to talk about motivation. We're here to talk about software enablement. We're not saying we've got hardware for these. Hardware is still 3 to 5 years away, but we need to have the software enabled and software stacks available for when the hardware's made available and devices are available. So we have the ARM A profile architecture, which is what I'm talking about today. This is ARM v8.0. You know, the main thing we added there was the 64-bit architecture. Crypto was the other big new feature. And since then, we have continuously improved it. 8.1 came along. VHE is the virtualization host extensions, support for, or improved support for type 2 hypervisors, atomics support for, further support for atomic operations over and above what was in 8.0. 8.2 adds RAS, reliability, availability, serviceability, statistical profiling, which is a debug feature, half precision floating point. We then came up, and we've already heard mention today of SVE from Fujitsu's A64FX, I believe the core name that George showed. SVE, scalable vector extension, and then 8.3 pointer authentication, which I'll actually come back to in a bit. RCPC, which is another load store memory consistency, nested virtualization support, and 8.4 last year. Further crypto instructions, secure EL2, allowing a hypervisor type functionality on the secure side, and some tightening and formalization of the ARM memory model. And we've been doing this incrementally year after year. This isn't everything. There's many more features added to the ARM architecture. I think I counted up to 90 when I was running through trying to pull them all together. But they're all small increments, and this is what we're doing this year. Yet more small increments, seeing what's the need of the ecosystem, where the markets are taking us, and working with what our partners, including Linaro and Linaro's members, require. So here's an overview of ARM 8.5 features. This still isn't a complete list. There's, you know, it'd be good 2-3 slides to list everything, but these are the ones I'm going to be talking about today. Starting with memory tagging extensions, branch target identifiers, and going through as we go. And some of these are very small additions, as we'll see, and some are larger. They've all been worked through with the ecosystem. So one of the main topics of 2018 has been security and Spectrum meltdown. But actually, that's not the only security. Spectrum meltdown aren't the only security issues we're facing today. And before we start talking about some security features, I want to just make sure we've all agreed some definitions for what I'm going to talk about. That the vulnerability is the open door that allows an attacker in, and an exploit occurs when an attacker takes advantage of a vulnerability. And it turns out that 2018 is the 30th anniversary of the Morris worm, which was one of the first worms that gained notoriety, and that made use of buffer overflows. And here we are, 30 years later, and you look at the CVE database, and a substantial number of issues are still buffer overflows and use after free. So we think Spectrum meltdown is all 2018, is all new, but actually we're still suffering and dealing with issues that were first identified 30 years ago. And, excuse me, buffer overflows are when you access memory running out past the end of an allocation. So in the diagram of memory on the right, if you had your buffer from 8,000 to 9,000, and for some reason you tried to access 9,500, and that's a buffer overrun. And we're also talking about use after free, which is accessing freed memory through a stale pointer, a pointer that exists to memory even though you freed it. Many, many vulnerabilities in the CVE database are caused by these functions, these vulnerability types. So for ARM 8.5, we're introducing something called memory tagging extension. And memory tagging probabilistically detects memory safety vulnerabilities. So it enables you to update your software before the defenses are tested, so you can detect issues such as use after free and buffer overflows in the lab when you're developing or in the field when users are using your code. Because we see a lot of issues aren't detectable in the lab because you don't have enough inputs, you don't have enough stimuluses to your software. It takes a lot of different stimuluses to find all the issues. So how does this work? When memory is allocated or freed, it is given a tag. On the left here, all the memory allocations have been given a tag, using color also to help identify the tags. So the blue area has been tagged 4. And all accesses to memory must be made with the same tag on the pointer as the memory has been tagged with. It's a standard lock and key scheme. So for example, here are 2 good accesses. The access to 0828 is made with the blue 4 key, and that gets allowed through, and the 0x070 gets through. 0x07 up to 9010 is allowed through because they're using the same key that the lock has. This access, a buffer overflow, isn't allowed because the key of 0x06 doesn't match the lock of 4. And if we then go and free memory, as we free the memory, we change the lock. So the now stale pointer would fail if we try and use that to access that memory. So we detect the use after free. So what's the use of this? How do we use it? So we believe tag checking can be introduced incrementally. Deploying memory allocator, so your malloc, your JEalloc, whatever your libc's memory allocator is, updating that to understand MT, and then just deploying that on your system will give you guards of your heap allocations. Stack and buffer overflows stack and global checking requires you to upgrade your compiler, and we are working on compilers and we'll be upstreaming those at some point, and Romana can talk further about that, and we'll be talking in the toolchain working group about plans for that as we go through this week. And this has been aimed, and the priority here for us is on checking memory allocations in the unsafe languages such as C and C++. Yes, there are languages that give memory safety or attempt to give memory safety, but we still see a large usage of C and C++, and that's the locations we're trying to aim for. And you can view MT as on-device hardware acceleration of tools such as the excellent address sanitizer. If you talk to various people doing large-scale software developments, they could say they'll run address sanitizer on their code base and their systems, and they'll be finding bugs every week. And this helps us find those bugs quicker because address sanitizer is very difficult to deploy in the field. Address sanitizer has a many X times, 3, 4 X times at least overhead. MT, the memory tagging, has a lower overhead, so it can be used in production environments. As I said earlier, it is probabilistic But if you're deploying it in large-scale deployments, the probabilities tend to that you're going to find these issues. You're going to find your vulnerabilities. And finding your vulnerabilities before they get attacked means that you don't get attacked, you get to fix early, and ultimately, as we all know, finding and fixing vulnerabilities and software issues, the earlier you can fix them, the cheaper it is in terms of effort and cost to fix those issues, rather than having to fix them when they've become a full-scale attack vector and being used to be as an attack vector. So memory tagging is all about detecting vulnerabilities and trying to help stop allowing an attacker in. But an attacker is, let's assume an attacker is going to be able to find a way in. What can we do to help prevent that attacker having an exploit, having a large surface of exploits available? So in 8.3, we introduced pointer authentication. Pointer authentication, one of its uses is as a strong defense against ROP attacks, return-oriented programming. ROP works by an attacker gaining access to your code and using gadgets in those code and corrupting your return address so that it can chain bits of code together to do what the attacker wants, not what you originally intended the code to do. Pointer authentication enables you that when you enter a function you sign, you add a pointer authentication part to your link register, you sign your link register, and when you return from that function, you authenticate the address you're returning to, and if the authentication fails, you get an exception. So that prevents someone jumping halfway into your function and using the wrong return address, and therefore reduces the return-oriented programming surface. And that was introduced in 8.3. In 8.5, we're introducing a complementary technology called branch target identifiers. And these are aimed at reducing the viable jump-oriented programming gadgets, JOP gadgets. And the way this works is that, as you see, under good, there's a BTI instruction. We mark pages as containing BTI, and then indirect branches can only branch to the locations which we've identified as being good locations for indirect branches by the BTI instructions. So this green line is good because the BLRX0 is going to a BTI. The C stands for cool, so it's a cool, a BLR, and that's fine. But this would cause an exception because you're branching to a move instruction in a BTI page, and a move instruction isn't a BTI instruction, and that would cause a fault. We don't do this on direct branches because direct branches are to a fixed location. It's the indirect branches where this needs to be protected. So we see branch authentication, pointer authentication and branch target identifiers as working together. So we did some research internally, and there's external research that's been done as well by other groups that return similar results. And basically, we see that while PAC and BTI don't get rid of all the gadgets that are possible, they make a significant reduction. This is looking at Ubuntu 14.04's glibc and the gadgets in there, glibc being a prime target for people to attack because of some of the things it can do. And we see a massive reduction. And also what we see is that the length of gadgets increases. And as the length of a gadget increases, that gadget will be doing more, and it'll be doing things that an attacker isn't able to control. It makes the gadgets less stable, which is why we've restricted this table to gadgets of less than 10 instructions. And many of the remaining gadgets are actually whole functions. So you're actually executing whole functions, and those become gadgets, which they were anyway. And as I said, this is ARM data. What's interesting, excuse me, of the job with PAC BTI reduced to 11 gadgets, we did some investigations of those, and only 2 of those are what are called dispatcher gadgets, which is what an attacker would use to control his attack and dispatch to other gadgets to execute his attack. And one of those, by changing the compile time options to stop allowing jump threading, it stopped being a dispatcher gadget. And the other one, you could go and look at your source code and make an effort to rewrite, and that would stop it being a dispatcher. And yes, there's still manual intervention required, but when it becomes 2 gadgets that you need to look at, or 11 gadgets, that's manageable. Whereas when you're looking at nearly 6,000 gadgets, that's an awful lot, and you can't go and catch every issue. So again, pointer authentication, branch target identifiers, reducing the exploitable surface. Sorry, one thing I would say here, and the deployment for these is that the instructions for what we've talked about are all in the no-op space. So actually you could write code or compile code today with compilers that support pointer authentication and when it's available branch target identifiers. And the code will run on a v8.0 machine, a v8.2 machine, and the instructions would act as no-op. So you won't get any added security, but the code will run and act as it should run. Then once 8.5 machines are available and devices are available, that same code would start executing those security parts, and you'll get the protections from pointer authentication and branch target identifiers. Excuse me. So the question was, do we have those instructions for 32-bit? The answer is no. I think. No. I was just checking with Romana. So those were 2 of the larger features we're adding, enhancements. Moving on to a selection of smaller features and enhancements. Starting with random number generation instructions. What I like is that you say it's a random number generator, it's got a true random number generator, a deterministic one, you know, the things, and then there's this alphabet spaghetti of standards that it's got to comply with. But basically, it's a random number generator provided by a couple of instructions from the CPU. Another security related topic, and this one's actually related to Meltdown. As I'm sure many people in this room are aware, the way we have been protecting against Meltdown has been through KPTI, kernel page table isolation. And this is all well and good, except that it prevents access from user space to the SP and self-hosted trace buffers. And when you wanted to do trace and SP, that's a bit of a problem. So we've added in 8.5 support to say that EL0 can't access the TTBR1 space and give a translation fault, and it gives a translation fault when it tries to do that. And that enables us not to need KPTI, because then your access to trying to access your kernel address map, your Linux kernel address map, always faults in a constant time. It doesn't matter whether that page was actually mapped in or not. There's a constant time fault, which is what Meltdown was making use of, the fact that that fault wasn't a constant time. Moving on again. As I said, 8.5 is full of many different features. Some are larger, some are smaller. This one is about JITs, and when you're optimizing code that is already running. And technically, the behavior up to now has been undefined in the ARM architecture, except that all CPUs have done the right thing, as we're about to say what the right thing is, and we're just now defining that right thing. So what we're trying to do is that an executing processor will run this code path repeatedly, and your JIT will see that that's hot and decide that it wants to optimize that code, and it wants to optimize it running in another thread on another processor whilst you're still running your code, so that you don't see any stoppages, your code doesn't stop running whilst you're still optimizing. So you have this code, and the first thing you do then is the modifying processor will compile and write a new routine, optimized routine in memory, and flush the cache. And at the end of that routine, it will put a branch back to the original code where it wants to re-enter the code sequence. Then, the modifying processor will write a branch to that new optimized routine in memory and flush the cache. So that once the executing processor notices that flush and picks up the change in memory, this is the sequence you should get, that you go to that new memory and run the new optimized routine. So the point is that we have now made sure that 1 and 2 are ordered, so that once you've written, if you've written and flushed your code, flushed the code out, and then you write the branch and flush that out, you can guarantee that you will get the new code when you do that branch. And now, this isn't a problem on any previous core, and this we said needs to be true of any new CPU produced. But this is behavior we've all been expecting to work and to behave like this. But actually, there was corner cases in the ARM architecture where technically it could have been undefined behavior. And so we've cleared that up and tidied that up to make sure this works as people expect. There's already been discussions this morning, moving on yet again to yet another completely different topic, about porting and running code and making sure code runs in multiple architectures. And different architectures handle conversions from floating point to integer differently. For numbers that are out of range, you can't represent in an integer. For not numbers, and normally this difference isn't very important because we're handling numbers that are in range and we can represent, and that matters. That's easy. That everyone agrees on how to do that. It's the extremities where people have differences. But there are cases where this difference in behavior produces a difference in behavior of programs, and that's not what you want if you're porting your code from one architecture to another. So again, 8.5 adds a couple of instructions to provide that alternate behavior on ARM to enable you to port your code and expect the same behavior, if that bit of code matters for you. Moving on, added various virtualization efficiency improvements. So some of the coarse-grained EL2 traps have been split up into multiple trap groups, basically taking feedback from the community about how often they were trapping to EL2 when various cache registers or iCache instructions were executed, and reducing the number of traps that are needed, speeding up your virtualization environment. So we've got now, as it says, separate EL2 traps for these various things. Content synchronization on exception entry and exit. So when you take a service call, a hypervisor call, whatever, and you go up an exception level, you enter an exception level, that's a context synchronization event. That means various things are flushed, registers are updated. Go and read the ARM glossary for exactly what happens. There's a lot of things that happens. But actually the feedback we got was that for some environments, this is unnecessary. You don't always need to do a complete context synchronization on entry to, let's say, a hypervisor that's just there to do a lightweight management of your system. So V8.5 adds the ability for you to control whether you want to do a full context synchronization or not, or you don't want to do a context synchronization on an exception entry. And if you don't do one, then it's up to you to make sure you put in the appropriate barriers within your exception handling code to make sure that if you do need things to have been synchronized, that they are. Now, for Linux, this isn't going to be used because Linux needs full context synchronization because of how it's designed. But this is for other environments where we've had conversations with other operating system vendors and operating system designers. And finally, cache clean to point of deep persistence. So if you have a system involving persistent memory, it has this concept of a point of persistence. When is the data actually persistent? When is it going to last beyond a power cycle? And in YVR18-104, we actually introduced an instruction to do a data cache clean to that point of persistence. But we've noticed, talking to the industry, the storage industry, that they've moved forward to actually identify 2 points of persistence. There's the point of persistence, which is basically the point at which actually memory might not be completely persistent, but there's enough energy left in the system that if you pull the plug out, that remaining energy will push all that data to the point of into your persistent memory. And then there's the point of deep persistence, where actually even that energy that's remaining in the system after you pull the plug out, even that could fail and the data is persistent. So that's when it's really in your persistent memory. 8.5 introduces a cache clean to this point of deep persistence. And you know, that's just been a very whistle-stop tour through the A-profile architecture. This is 8.4. There's 3 of the big things, or what I thought were the big things for 8.5. As you see, there's a lot of other little things as well. We are working and will be pushing bin utils patches upstream in the imminent future. We're working on libc changes. We're working with the community on those. We'll be updating the LLVM and GCC and the Linux kernel as we move forward. And what I am pleased to announce is that this screenshot is out of date. So if you want to go and look at the instructions that we've added and the system registers we've added, you can go onto our developer website today and go and download these. I'm really pleased with this. It's the first time we've been able to say the instructions and the system register descriptions are available on the same day that we announce the architecture. It's not the full ARM. The full ARM is probably 6 months away still, but that's got to go through more iterations. There's a lot more work that's involved in pulling together the full text for the ARM. So what I hope I've shown is that we're adding useful bits, the motivation, useful bits to the architecture to move us forward to meet changing market requirements. Security's been that big issue through the year that was taking that seriously, and it's not just Spectrum meltdown, but it's also the issues that have been with us for 30+ years and moving forward, and other little things in the ARM architecture that are just needed to keep support for the ecosystem and provide support that the ecosystem needs. So with that, thank you very much, and allow any questions. So Romana, there's only one mic and it's near the front, so if Romana would stand up and hold the mic, if you come and talk to Romana here, he'll hand you the mic, so if you, or Romana will do the running. Grant.
Matt, can you give approximate timelines when hardware is going to show up with the new revisions?
So hardware generally takes 3 to 5 years. So then this is why we're talking today. It's about software enablement to make sure the software's ready. Their CPUs will take a couple of years, and then you've got a year after that. I can't talk about our CPU roadmap today, and I certainly can't talk about what people will build, because
That's why I asked approximately.
yeah.
Yeah, I have a bunch of questions, but I'll just to pick two. SMC calls from EL0, is that going to be something you guys are looking at soon? And for the random number generator, do you guys have some sort of way of doing runtime checking to make sure that any entropy sources and things like that are actually have not failed to get that the randomness still is cryptographically safe?
Okay, so SMC calls, can I talk to you offline? We haven't got them in the architecture, and I don't think there's a plan. There's not currently a plan to add them, but I'm happy to talk to you offline as what you see the use cases and why you'd want that. So let me try and get back to the right side. So the way this works is you've got the true random number generator providing entropy, and then your deterministic random number generator, but you can then reseed your DRNG from your TRNG, and part of what you get there is you get a result which says, actually, go away and come back later because I haven't got enough entropy, right? You have to go away and do something else because I've not got enough entropy, and then it waits for that, and then you come back and you try again. So over there, sorry.
So with the fixes that we had for Spectrum Meltdown, they were basically vulnerabilities that came out of speculative execution, which at the heart of it is adding a lot of complexity to a system to aid performance. So there was a complexity source that added performance. Obviously, a lot of these features are adding security, like PAC, BTI, but it's still adding a lot of complexity. Like a lot of these features add complexity, and the complexity in itself becomes an attack surface. Like where's the corollary toward all these architectural features that get added, where you ramp up the testing and kind of the combinatorial testing of all these features together in a system and go, actually, we haven't created some monster new attack surface, because kind of security by simplicity seems an easier path than security by layer cake.
So, yes, you can go back to simplicity. My argument would be you could take out all your, if you really wanted to, you could take out all those performance enhancements and go back to the 1980s, if you really wanted to. But yes, it does add complexity. So we do a lot of testing internally. So ARM CPU teams, when they're building CPUs, do an extreme amount of testing. There's a mix of formal and directed tests and other things. We do have a compliance suite on the architecture to test that, and we do look at how the different bits interact. I was going to say something else about software testing that goes in there, but I can't remember what I was going to say now, so I won't. Because, have you got something to say, Ramona? Yes.
So, I mean, sorry. So these are mitigations for different forms of attacks. So yes, you're right that if you combine them, you could be creating theoretically a new attack surface. But to some extent, it's a bit of a reactive game. This in some sense is going after the Morris worm, as Matt said earlier. It's providing the basic level of security. We've got to take care of buffer overflows. We've got to take care of use after freeze and things like that. And if we don't fix that, well, what's the point in going after looking at Spectrum Meltdown? We need to first fix the basics, cut down the attack surfaces where we can, and then look at the next thing. It is an incremental process. There's no magic bullet here, in my personal opinion.
So I have remembered what I was going to say now. So MTE, you can view as sort of crowdsourcing debugging. It's about debugging on a large scale and running that and finding those vulnerabilities earlier. And it's about detection. So in theory, that shouldn't be an increase of surface. That really is a help. But also, so you might have heard us talk about platform security architecture, certainly in the M profile space and deeply embedded space. And that's all about things like threat models and working out what actually are my threats. And actually bringing that sort of rigor to the whole system is something we're working on. And that's not necessarily in architecture, as in his instructions, but it's in architecture as in how do you think about your design. Mr. Masters, since you've got the mic. Nice tattoos, by the way.
Sorry?
Nice tattoos, by the way.
Oh, yeah, yeah. Well, I ran back from my run because I didn't want to miss you. Figure I'll shower later. So sorry I smell, Rama, but you're the only one who has to smell me. So anyway, so I had one observation and one question. So one observation that just came to me a few minutes ago is a lot of people think we're going to turn off PTI. It's a temporary thing, and we're going to get rid of it over time. Certainly I hear that from all the architecture companies where they've had to implement it. And I've been going around behind the scenes saying, I think PTI should live for a long time. We can talk about it offline, but I just want people to think there's another answer than just it's a short-term hack, we should get rid of PTI. I think there will always be address space de-randomization attacks or other meltdown type attacks found, and we should not. You can answer in a minute, we can follow up. I've got an actual question, and that is around the memory tagging.
Yep.
What we need to do with any of these new technologies that involve doing mass rebuilds, or, I mean, you've heard this from me before,
Yeah.
This is not a new statement from me, but I'm just raising it here. If there's something that's a many-year journey, those of us in the distro world, we have to get in now. We have to work on models, and we have to get this enabled, especially those of us who live in, is this being recorded?
Yes.
Okay. Especially those of us who live in the wonderful world of enterprise distros that are amazing and great and very fast-moving and very proactive and engaged and all the right buzzwords, not at all slow-moving in any sense, where there's a long tail. But if there were, then it would take us a very long time to get these technologies in. So, you know, just plugging saying, when we have to do a big lift, let's all do that now, rather than wait 5 years for the hardware.
But that's why we're out here. I'm up
Right,
here now,
yeah, I'm
is
saying
to
let's
say-
engage with you now. Yeah.
Yeah, it is about making sure you
And
we
also
can talk
that's
to you
why
now.
we try and push the support into the upstream tools as quickly as possible,
Cool.
given the timelines and the resources we have. So,
He wants to respond on the PTI.
okay, hang on. Let me do the PTI first.
Yeah, sorry, the E0 PDX thing are effectively a hardware implementation of page table isolation. The thing that may go will be the software implementation, and therefore, like as the slides mentioned, this enables SPE to be used in cases which are currently incompatible with the software PTI implementation and should allow for lower overhead. That's it.
See, this is why we have engineers who know more than me in the room.
So I was wondering if the DRNG can be seeded from anything other than the built-in TRNG, because you may trust it and not trust the true entropy instructions.
So the DRNG can only be seeded from the TRNG. I would argue that whilst you may trust it, it's about what the CPU trusts as well.
No, but the DRNG is deterministic, so you can validate that it does what you expect. And for a TRNG, that's not the case. So.
Absolutely, yeah. That is actually a problem that Intel was facing. So they have the exact same thing. And a lot of people do not trust Intel's implementation of the true random number generator, of the C that goes into the random number generator. Even they say, of course, that it is absolutely safe, and there's certainly no backdoor put in there by anybody. There are some people that do not believe them. And the same thing could potentially apply to anybody who implements one of your chips. Even if you know that your implementation is correct, somebody could have the license for the core and put in different implementation and might get an incentive from their local government to put in certain predictable random numbers.
Okay. So at the moment, there is nothing for that in 8.5. Sorry. Just... Any more questions? Any more questions? No. Cool. Thank you all very much.